Hey crew, it's Pitt, and I'm back with some more philosophy. Today we're diving back into the works of Mr. Georg Hegel. This is the science of logic. We are reading aloud and discussing as we go along the various points that are brought to light by the text. It's not the format for everyone, but people find value in it, so you are more than welcome to tag along as we continue our exploration. Before we begin, however, if you are unfamiliar with me, any of my unconventional beliefs, or if at any point in time I lose you in the terminology, there will be several playlists linked in the corner above and the box down below, along with the original source material, so that you can get a better understanding of who I am and why I say the things that I do. A particular note today is going to be exploring philosophy, where we talk about philosophy in some great detail. Some people seem to have the opinion that I don't know anything about philosophy, and that's quite funny. With that being said, we're going to dive in and continue our exploration of Georg Hegel, the science of logic, with Quantum Remark 2. This is another long one, y'all bear with me. Remark 2. The purpose of differential calculus deduced from its application. I did take the time to go and look up what calculus was. Right, the last time I wasn't familiar. I never studied calculus, and what it appears to be is the study of change, right? How to quantify change. So you take something that is moving, right, and you say, I am at this reference point, the thing moving is at this reference point, and you measure the distances according to a triangle, and then when it gets a little bit farther, you measure the distance again, and the difference between those tells you things. Calculus is the study of what is being told by the difference. Fairly interesting field of mathematics. I don't know that I would ever study it in depth, though. In the previous remark, we considered the conceptual nature of the infinitesimal, which is used in differential calculus, as well as the reason for introducing it in that calculus. Both are abstract determinations and therefore also intrinsically easy. Its so-called application, however, presents more serious difficulties, but also on the more interesting side. The elements of this side will be the subject of the present remark. The whole method of the differential calculus is covered by the proposition dx to the nth power equals nx to the nth power minus I dx, or f parenthetical x plus I minus fx divided by I equals p. That is equal to the coefficient of the first term of the binomial x plus d, x plus I, raised to the power of dx or I. There is no need to learn anything further. All right, we're wrapped up then, right? The derivation of the subsequent forms, or of the differential of a product, of an exponential magnitude, and so forth, follows mechanically. In a short time, half an hour or so, one can be in possession of the whole theory, and with the finding of the differential, the converse, or the finding from the differential of the original function, is equally given. What takes longer is the endeavor to see, to grasp conceptually, how it is that, after easily managing analytically, that is, purely arithmetically, one condition of the task, namely the finding of the said coefficient by the expansion of the function of the variable after the latter has received the form of a binomial by the addition of an increment. How? After this part of the task, the other condition, namely the omission of the remaining terms of the series except the first, can also be correct. If the coefficient alone were all that is necessary, then once this is determined, all the concerns of the theory would be taken care of in less than half an hour. As we said, the omission of the further terms of the series would present no difficulty. Far from it, for such terms as terms of the series, their determination as second, third, etc., function is already absolved with the determination of the first, would not come into question at all, since they are of no relevance. We may begin by remarking that the method of differential calculus has all the markings of not having been invented and developed for its own sake. Not only is it not grounded for itself as any other form of analysis, what is more is that the arbitrary direct omission of terms that have resulted from the development of a function, despite the fact that this whole development is taken to belong fully to the matter at hand, which is considered to be the difference between the developed function of a variable after this has been given the form of a binomial, and the original function, that this omission totally contradicts every mathematical principle. The need to proceed in this way, as well as the lack of internal justification for the procedure, immediately suggests that the origin and foundation must lie elsewhere. It happens also in other sciences that what is presumed at the start to be the primitive element from which the propositions of a science will have to be derived is in fact not self-evident, but proves rather to have its cause and justification in what follows. The course of events in the history of the differential calculus makes it clear that it originated in the various so-called tangential methods, its subject matter in ingenious devices, as it were. It was only later, when its method was extended to other subject matters, that the nature of this method came in for conscious reflection and formalization, and the attempt was made to raise its abstract formulas to principles. We have shown that the conceptual determinateness of the so-called infinitesimal is the qualitative determinateness of the quantity of such quanta as are first positioned in relation to each other. Attached to this, there came the empirical undertaking of discovering this conceptual determinateness in such descriptions or definitions of the infinitesimal as are found of it when they taken as infinitely small difference or the like. Can y'all hear the thunderstorm out there? I hope not. But the next question would be about the nature of the transition to mathematical formulation and application. To this end, we must first examine the theoretical side further. The conceptual determinateness, and this is a task which will prove to be not altogether unfruitful, even by itself. We must then consider the relation of this theoretical side to its application, and show in the case of both, inasmuch as it is relevant here, that the general conclusions are adequate to both the purpose of differential calculus and by the method by which it realizes it. First, we must remember that the specifically mathematical form of the concept now at issue has already been given in passing. The qualitative determinateness of quantity is first exhibited in the quantitative relation as such. However, already in the demonstration of the various so-called kinds of reckoning, see the relevant remark. Let's see if that is actually something. Yeah, see I'm not going back to the footnotes where it is just go look at this other part. It was demonstrations of the various so-called kinds of reckoning. It was anticipated that it would be in the relation of powers, still to be considered in its proper place. That number, by the equating of the moments of its concept, unity and amount, is posited as having turned back into itself, and that, as such, it would receive the element of infinity, of being for itself, that is, of being determined through itself. Thus, as already indicated, the explicitly qualitative determinateness of magnitude is essentially connected with the determinations of powers, and since differential calculus specifically operates with qualitative forms of magnitudes, the mathematical subject matter that specifically belongs to it must be the treatment of forms of powers. It is also the whole range of problems, together with their solutions, for the sake of which differential calculus is employed, which shows that its interest lies solely in the treatment of determinations of power as such. This is an important opening position. It at once puts in the forefront something determinate instead of merely formal categories of variable, continuous, or infinite magnitudes, or even only of functions in general. Yet it is still too general, for there are other operations that deal equally with powers. The raising to a power, the extraction of a root, also the treatment of exponential magnitudes and logarithms, of series, of equations of higher powers. The interest and the effort of all these operations lie solely in the relations based on powers. Undoubtedly, together, they constitute a system of the treatment of powers. But which of the various relations in which the determinations of power may be put is the proper subject matter and interest in differential calculus? This is to be ascertained from the differential calculus itself, that is, from its so-called applications. These constitute, in fact, the core of the matter, the actual procedure in the mathematical solution of a certain group of problems. This procedure came earlier than any theory or general part, and was called an application later, only in connection with the then created theory, the intention of which was, in part, to draw up its general method for the procedure, but in part also to find principles for it, that is, a justification. We have shown in the preceding remark the futility of searching for principles that would effectively resolve the contradiction patent in the current conceptions of the method of calculus. We have shown this futility instead of excusing it or hiding it on the pretext that what is necessary for mathematical practice is, however, out of consideration here, or what amounts to the same thing, with the possibility of an infinite or arbitrary approximation to the infinite or the like nonsense. These principles, and all the fuss made on their behalf, if the general method of this real part of mathematics is called differential calculus, were abstracted differently than it has been done so far, would turn out to be, indeed, just as superfluous as they are inherently defective and irrevocably contradictory. If we investigate what is distinctive about differential calculus by the simple inventory of what there is in this part of mathematics, we find the following as the subject matter. I think that's delta. I'm not positive. I still have not learned the Greek alphabet. Equations in which any number of magnitudes, here we need simply confine ourselves to 2, are combined into one determinate whole in such a way that, first, the equations themselves derive their determinateness from empirical magnitudes, which are their fixed limits, and also from the kind of link which they have with these limits, and with each other, as is generally the case in an equation. But since there is only one equation for both magnitudes, and relatively more equations for more magnitudes, but always less than the number of the magnitudes, these equations belong to the class of indeterminate equations. And second, one feature of the determinateness of these magnitudes, or of one of them at least, is that these magnitudes occur in the equation with a power higher than the first power. A few observations in this regard are in order here. The first is that the magnitudes in the first of the above 2 headings exclusively have the character of such variables as occur in the problems of indeterminate analysis. Their value is indeterminate, but if a completely determinate value accrues to one of them from elsewhere, that is, a numerical value, then the other also becomes determinate, so that one is a function of the other. For the specific magnitudes here at issue, therefore, the categories of variable magnitudes, of functions, and the like, are merely formal, as we said earlier, because they are still too general to contain the kind of specificity to which the whole interest of differential calculus is directed. Nor can this specificity be developed out of it analytically. They are, as such, simple, insignificant, easy determinations that are rendered difficult by importing into them that which is not in them, in order, then, to derive it from them, namely, the specific determination of differential calculus. Then, as regards the so-called constant, it should be noted that it is at first an indifferent empirical magnitude, determining the variables merely with respect to their empirical quantum, as a limit of their minimum and their maximum. But the nature of the link connecting the constants to the variables is itself one factor defining the particular function which the magnitudes are. But conversely, the constants themselves are also functions. For instance, inasmuch as a straight line carries the meaning of being the parameter of a parable, this, its meaning, is that it is the function y squared over x, as in the expansion of a binomial generally. Binomial. The constant, which is the coefficient of the first term of the expansion, is the sum of the roots. The coefficient of the second term is the sum of their products in twos, and so on. Hence, these constants are here in general functions of the roots. Where, in integral calculus, the constant is determined from the given formula. It is, to that extent, treated as a function of that formula. We shall further consider these coefficients later on, but in another determination than that of functions, their concrete meaning being the real point of interest. Now, the essential difference between variables are considered in differential calculus, as they are in indeterminate problems, lies in what has just been said. Namely, that at least one of those magnitudes, or also all of them, is in a power higher than that of 1, though it is again a matter of indifference whether they are all of the same higher power or of unequal powers. The indeterminateness specific to them consists solely in this, that in such a relation of power they are functions of one another. The alternation of the variables is thus qualitatively determined and consequently continuous, and this continuity, itself again only the formal general category of an identity, of a determinateness preserved, unaltered in the alteration, has its determinate meaning here, solely in the power relation which does not have a quantum for its exponent, and constitutes the non-quantitative, permanent determinateness of the ratio of the variables. It is, therefore, also to be noted, this time against another form of formalism, that the first power is a power only in relation to higher powers. By itself, x is just an indeterminate quantum. Thus, there is no point in differentiating for their own sake the equations y equals ax plus b, the equation of the straight line, or s equals ct, that of an absolutely uniform velocity, if from y plus ax, or also from y equals ax plus b, we obtain a equals dy over dx, or ds over dt equals c. From s equals ct, then a equals y over x is equally the determination of the tangent, or s over t equals c, the determination of simple velocity. This last is expounded as dy over dx in the context of what is said to be the expansion of uniformly accelerated motion. But that there would occur in the system a moment of simple, absolute uniform velocity, that is, one not determined by the higher power of one of the moments of the motion. This, as remarked earlier, is itself an empty assumption based solely on the routine of the method. Since the method has its inception in the representation of the increment which the variable is supposed to sustain, then of course a variable which is only a function of the first power can also sustain an increment Now, in order to find the differential, we have to subtract the difference of the second equation, thus produced from the one given. The emptiness of the operation becomes obvious, for the so-called increment is the same for all the alterable terms themselves. Beta. We have identified the nature of the equation, which we want to treat. Now we must declare the interest that motivates our treatment of it. This consideration can only yield known results, especially in the form in which they are found in Lagrange's version. But in my exposition, I have restricted myself to basic elements in order to eliminate from it any heterogeneous material otherwise mixed with it. The patent basis for the treatment of an equation of this kind is that the power is taken to be a relation inside itself, a system of relational determinations. We said earlier that power is number which has attained a state at which it determines its own alteration. Its moments, unity in amount, are identical, perfectly identical, as previously demonstrated. First of all in the square, and a point of no consequence here, formally identical in the higher powers. Now, since as number the power is an aggregate, even if one prefers the expression magnitude because of its greater generality, in itself, power still is always a number, and is also presented as a sum. It can be directly broken up internally into an arbitrary grouping of numbers that have no other determination with respect to each other and to the sum, except that together they equal the latter. But the power can also be divided into a sum of distinct terms, determined by the form of the power. If the power is taken as sum, then its radical number, the root, is also taken as a sum. Arbitrarily, after repeated division, the manifoldness as something indifferent, empirically quantitative. The sum, which is supposed to be the root, reduced to its simple determinateness, that is, its true generality, is the binomial. Any other increase of the terms is a mere repetition of the same determination and therefore something empty. What matters here is only the qualitative determinateness of the terms which result from the raising to a power of the root taken as sum, a determinateness which lies solely in the alteration which the potentiation is. Consequently, these terms are wholly functions of the potentiation and of the power. Now, this exposition of number as the sum of an aggregate of terms, which are the functions of the potentiation, added to the interest in finding the form of such functions, and also this sum from the aggregate of the terms, in so far as this find must depend on that form alone. This, as we know, constitutes the special theory of series. But it is essential here that we distinguish another source of interest, namely the relation of the underlying magnitude, of which the determinateness, since it is a complex, that is, an equation here, includes in itself a power, to the functions of the raising of it to a power. This relation, taken in total abstraction from the just mentioned interest of the sum, will prove to be the only intended point of view of differential calculus, which is, in fact, realized by the science. But we must first add one more determination to what has been said, or better, remove one which is there. For we have said that the power enters into the variable determination of a magnitude, which is regarded as a sum inside itself. In fact, a system of terms insofar as these are functions of the raising to a power, and that the root is also thereby regarded as a sum, in the simply determined form of a binomial. x to the nth power equals parenthetical y plus z to the nth power equals parenthetical y plus ny n to the nth power minus I z plus ... This exposition was all right for the expansion of the power, that is, for obtaining the functions of its being raised to a power from the sum as such. But the issue here is not a sum as such or the series arising from it, but only the connection to be taken from the sum. All that remains after the plus of a sum as sum is abstracted from is, on the one hand, the connections as such of the magnitudes, and, on the other hand, all that is needed for the finding of the functions of the expansion of the power. But that connection is already determined by the fact that the object here is an equation. Y to the mth power equals ax to the nth power. Already a complex of several variable magnitudes, which contain a power determination of them. In this complex, each of these magnitudes is posited simply as connected with the others, as a function of the other magnitudes, each carrying, as one could say, a plus in it. This plus determination is given to them by their character as functions of one another. But precisely for this reason, the determination is totally indeterminate, is not an increase or an increment or the like. Yet, even this abstract point of view could be left out of account. We can quite simply stop at the point where, since in the equation the variables are given as reciprocal functions in a determinateness which thus contains a relation of power, also the functions of the raising to a power of each are now compared with each other, and these second functions are determined by nothing else except the potentiating itself. At the start, to convert an equation of the powers of its variables into a relation of the functions of its expansion can be said to be a matter of choice, or a possibility. Only some further purpose, need, or use has to step in to indicate the usefulness of such a transformation. The transposition was occasioned by its usefulness alone. When we began just now with the exposition in a magnitude which is taken as an internally differentiated sum of these potentiating determinations, this served only in part to indicate of which kind such functions were. In part, it was the way of finding them. What we have here is an adaptation for the purpose of differential calculus of the usual analytical form of development, an increment. dx, I, is assigned to the variable, and then the power of the binomial is expanded by the terms of the series belonging to it. But the so-called increment is supposed to be not a quantum, only a form, the whole value of which is that it assists in the development. It is admitted, notably by Euler and Lagrange, and in the representation of limit earlier cited, that what is wanted are only the resulting power determinations of the variables, the so-called coefficients, namely of the increment and its powers, according to which the series is ordered and to which the different coefficients belong. It may be noted in this connection that since an increment with no quantum is being assumed here only for the sake of the development, it would have been more suitable to take I, the unit, for that purpose. For that increment constantly recurs as a factor in the development, and the factor of 1 fulfills precisely the purpose of having an increment without any quantitative determinateness or alteration being posited thereby. Whereas dx, burdened as it is by the false representation of quantitative difference, and other signs such as I, burdened for their part by a show of generality that is here pointless, always have the semblance and the pretension of a quantum and its powers. And the pretension, despite its being just that, brings with it the trouble of removing and omitting what is pretended. In order to retain the form of a series expanded on the basis of powers, the designation of the exponents as indices could just as well be attached to the one. But in any case, abstraction must be made from the series and the determination which the coefficients have according to the place they occupy in it. The relation between all of them is the same. The second function is derived from the first in exactly the same manner as this is derived from the original. And for any function counted second, the one derived first is again the original. But the essential point of interest is not in the series, but solely in the determination of the power that results from the expansion, as related to the magnitude, which for the power determination is immediate. Therefore, instead of defining it as the coefficient of the first term of the development, for a term is designated as the first with reference to the others that follow it in the series, but any such power as that of an increment, like the series itself, has no place here. The plain expression, derived function of a power, or the just said function of the raising of the magnitude to a power, would be preferable. These are expressions which presuppose that the derivation is a development falling within a power. Now, if the strictly mathematical beginning in this part of the analytic is nothing more than the finding of the function determined by the expansion of the power, the next question is what to do with this relation thus obtained. Where does it have an application and use? In effect, for what purpose are such functions sought? It is because of relations in concrete objects, which allow reduction to those abstract analytical functions, that differential calculus has become the source of great interest. But, as regards the question of the application, this much follows directly from the nature of the fact itself. Because of the form which the moments of a power assume as demonstrated, without having to infer it from individual cases of the application itself. Namely, the development of the magnitudes of the powers that yield the functions of their potentiation entails at first abstraction made of a more precise determination, simply the reduction of their magnitude to the next lowest power. This applicability of this operation is to be found, therefore, in connection with objects in which there is likewise present such a difference of power determinations. Thus, if we reflect on the properties of space, we find that space has three dimensions, which, in order to distinguish them from the concrete abstract differences of height, length, and breadth, we can call concrete. They are, namely, line, plane, and total space. And if we take them in their simplest form and with reference to self-determination and consequently to analytical dimensions, we then have a straight line, plane surface, and surface as square and as a cube. The straight line has an empirical quantum, but with the plane there enters the qualitative element, the power determination. More detailed considerations, e.g. that the case extends to a plane curves, we can leave undiscussed, for we are concerned primarily with the distinction in general. It is here that the need also arises to pass from a higher power to a lower and vice versa, when, for instance, linear determinations are to be derived from given equations of the plane, etc., or vice versa. The motion, further, in connection with which we have to consider the quantitative relation of the space traversed to the time elapsed in traversing it, assumes the various determinations of a simply uniform motion, a uniformly accelerated one, and one which is alternatively uniformly accelerated and uniformly retarded, motion that turns back upon itself. Inasmuch as these various species of motion are expressed in accordance with the quantitative relation of their moments of space and time, we have for them equations of various power determinations, and inasmuch as the need arises to determine one species of motion, or also of spatial magnitudes, to which a species of motion is associated, from another species of motion, such an operation likewise entails the transition from one power function to another, whether higher or lower. These two examples will suffice for the purpose for which they were adduced. The semblance of arbitrariness to which differential calculus gives rise in the course of its application would already be brought under control by a consciousness of the nature of the areas in which an application can be made, of the particular need for the application, and the condition under which it is made. But now, it is also within these same areas that one gets to know between which terms of a mathematical problem such a relation occurs as is properly posited by differential calculus. It must be noted, first of all, that two relations are at issue here. The operation of lowering the degree of an equation, considered according to the derivative functions of its variables, yields a result which, in itself, no longer truly is an equation, but is a relation. It is this relation which is the subject matter of differential calculus proper. Also given with it, secondly, is the relation of the higher power determination itself, the original equation, to the lower, the derivative. This second relation we must leave aside for the time being. It will be proved to be the subject matter of integral calculus. Let us start by considering the first relation, and for the determination of the moment in which the interest of the operation lies, the moment to be derived from the so-called application. Let us take the simplest example, that of curves defined by an equation of the second power. As we know, the relation of the coordinates is directly given by the equation in a power form. From the fundamental determination, there follow the determinations of the other straight lines linked to the coordinates, the tangent, subtangent, normal, and so on. But the equations between these lines and the coordinates are linear equations, the wholes of which these lines are determined as parts are right-angled triangles formed by straight lines. The transition from the original equation in power form to these linear equations involves, now, the said transition from the original function. That is, one which is an equation, to the derived function, which is the relation, specifically, between certain lines contained in the curve. The problem is to find the link between the relation of these lines and the equation of the curve. It is not without historical interest to remark this much, that the first discoverers only knew how to report their findings in a wholly empirical manner without being able to give an account of the operation, which remained something completely external. I shall limit myself in this regard to citing Barrow, Newton's teacher, in his lecture Optimum de Geometry, where he deals with the problems of higher geometry according to the method of the indivisibles, a method which at first diverges from what is most characteristic of differential calculus. He also gives an account of his procedure for determining the tangents, because, as he says, his friends so urged him. One must read for oneself how he sets up his problem to have the proper idea of this procedure. It is formulated wholly as an external rule, in the same style as was once, in the school books of arithmetic, the rule of 3, or better still, the so-called test of 9 for the 4 operations. He draws the tiny lines on which were later called the increments in the triangle characteristic of a curve, and then gives the instruction, as a mere rule, to eliminate as superfluous the terms which, as a result of the expansion of the equations, turn up as the powers of such increments, or as products, not reading the Latin. Similarly, to omit the terms which contain magnitudes only determined by the original equation, a subsequent subtraction of the original equation from the one construed with the increments. And finally, to substitute for the increment of the ordinate itself, and for the increment of the abscissa, the subtangent. The procedure, if one may say so, could not be laid out in a more schoolmasterly form. The last substitution is the assumption of the proportionality of the increments of the ordinate and abscissa to the ordinate and subtangent, which is the ordinary differential method, is made the basis for the determination of the tangent. In Barrow's rule, this assumption stands out in all its naive nakedness. A simple way of determining the subtangent was found. Roberval's and Fermat's artifices follow a similar course. The method for finding maximal and minimal values from which Fermat started rest on the same basis and the same procedure. To find so-called methods, that is, rules of that kind, was the obsession of the time, and also to make a secret of them, which was not only easy, but in one respect also necessary, for the very reason that made it easy, because the inventors had found only an empirical external rule, not a method, that is, nothing derived from recognized principles. Leibniz was indebted for such a so-called methods to his contemporaries, and Newton was also indebted to them, even though he received them directly from his teacher. By generalizing their form and range of application, they opened up new paths for the sciences. But in this, they also felt the need to wrest the procedure free of the shape of the external rules. They sought to give it to the necessary justification. If we now analyze the method more closely, this is how it actually proceeds. First, the power determinations, understood, of the variables contained in the equation are reduced to their first functions. But the value of the terms of the equation is thereby altered. There is no equation left, therefore, but what has arisen is instead only a relation between the first function of one variable and the first function of the other. Instead of px equals y squared, we have p 2y. Or instead of 2ax minus x squared equals y squared, we have a minus x equals y, which it later became common to designate as the relation dy over dx. The equation is that of a curve, whereas this relation, which is totally dependent on it and is derived from it above according to a mere rule, is a linear relation with which certain lines are in proportion. P to y, or a minus x, y, are themselves relations of the straight lines of the curve, the coordinates, and the parameters. However, with all this, nothing is as yet known. The point of interest is to know, regarding other lines connected with the curve, whether that derived linear relation applies to them, to find out the equality of two relations. Second, this is therefore the question: which are the straight lines determined by the nature of the curve? Which stand in this relation? But this is what was already known, namely, that a relation obtained in this way is the relation of the ordinate to the subtangent. This the ancients had found out in an ingenious geometrical manner. What the moderns have discovered is the empirical procedure for setting up the equation of the curve in such a way that it will yield the first relation of which it was already known, that it is equal to a relation containing the line to be determined, here the subtangent. Now, on the one hand, the setting up of this equation, the differentiation, has been methodically conceived and methodically executed. On the other hand, the imaginary increments of the coordinates, and the imaginary characteristic triangle formed by them, and an equally imaginary increment of the tangent, were invented in order to present the proportionality of the ratio, which was obtained by lowering the degree of the equation to the ratio of the ordinate and the subtangent, not as something just picked up empirically from something already known, but as demonstrated. However, in the external form that the cited rules assume, this already known something proves to be everywhere and unmistakably the sole occasion and justification for the assumption of, respectively, the characteristic triangle and the said proportionality. Lagrange was the one who did away with this pretense and pursued the genuinely scientific way. It is to his method that we owe the insight into the decisive point, for it consists in separating the two transitions required for the solution of the problem, and in proving each by treating it by itself. The one side of this solution, inasmuch as, for the sake of detailing the steps involved, we restrict ourselves to the elementary example of the problem of finding the subtangent. The theoretical or general part, namely, how to find the first function from the given equation of the curve, has its own internal rule. This part yields a linear relation, hence a relation of straight lines that occur in the system defined by the curve. The other parts of the solution now consist in finding the lines in the curve that enter in such a relation, and this is now done in a direct manner. That is, without the characteristic triangle, which means without assuming infinitely small arcs, ordinates, and abscisses, and without attributing to these the determinations of dy and dx, that is, of the sides of that relation, and at the same time immediately the meaning of the equality of this relation with the ordinate and the subtangent themselves. A line, like a point also, obtains determination only in so far as it constitutes the side of a triangle, and the determination of a point also lies in that. This, I may mention in passing, is the fundamental proposition of analytical geometry from which the coordinates of that science are derived, just as from it the parallelogram of forces is derived in mechanics. It amounts to the same thing. For which reason the many efforts to find a proof for it are quite superfluous. The subtangent is now posited as the side of a triangle, the other sides of which are the ordinate and the tangent connected to it. The equation of the latter, as a straight line, is P equals AQ. Adding plus B is needless, but it is done only out of a fondness for generality. The determination of the ratio P over Q falls within A, the coefficient of Q, which is the respective first function of the equation, but may simply be considered as A equals P over Q. And this is, as we said, the essential determination of the straight line applied to the curve as tangent. Since now, further, the first function of the equation of the curve is taken to be equally the determination of a straight line, and since P, the one coordinate of the first straight line, and Y, the ordinate of the curve, are assumed to be the same, we assume, therefore, that the point at which the first straight line taken as the tangent touching the curve is equally the starting point of the straight line determined by the function of the curve. Then, all comes down to showing that this second straight line is congruent with the first, that is a tangent, or algebraically expressed, that since y equals fx and p equals fq, assuming that y equals p and hence fx equals fq, also f, I'm not sure what that divisor is right there. It is some mathematical equation, I'm sure. F whatever x equals f whatever q. Is that a division sign? Because that is not a standard division sign. I'm not sure what that is. If you know, let me know. Now, At the straight line applied as tangent, and the straight line determined from the equation by way of its first function coincide, that this last is also tangent, this is demonstrated with the aid of the increment I of the abscissa and the increment of the ordinate determined by the expansion of the function. Here, also, therefore, the infamous increment steps in. However, how it is here introduced for the purpose just stated and how the functions is expanded with its aid must be distinguished from the earlier mentioned use of the increment in finding the differential equation and in the characteristic triangle. Its use here is both justified and necessary. It falls within the parameter of geometry, for it is of the definition of a tangent, as such, that between it and the curve with which it has a point in common, no other straight line can be drawn which also passes through this same point. For, as thus determined, the quality of tangent or non-tangent is reduced to a quantitative difference. The tangent is the line to which, with respect to the determination here at issue, the greater smallness accrues. This seemingly only relative smallness contains nothing empirical whatever. That is, nothing that depends on a quantum as such. It is posited as qualitative by the nature of the formula, whenever the difference of the moment on which the magnitude to be compared depends is a difference of power, since this difference comes down to I and I squared, and I, which after all is supposed to signify a number, is then to be represented as a fraction. I squared is in and for itself smaller than I, so that even the representation of an arbitrary magnitude in which I might be taken is here superfluous and in fact out of place. Precisely for this reason, the demonstration of the greater smallness has nothing to do with something infinitely small, for which there is thus no need to bring it in here at all. Even if only for its beauty and its well-deserved but nowadays forgotten merit, I must also mention Descartes' tangential method. It has, at any rate, a bearing on the nature of equations regarding which yet one more remark is to be made. Descartes expounds this independent method, in which the required linear determination is likewise found from the same derivative function. In his geometry, a seminal work in other ways as well, it is here that he taught the great basis of the nature of equations and their geometrical construction, and of the application of analysis, which he thereby greatly expanded in scope, to geometry. The problem takes with him the form of a task of drawing straight lines perpendicularly to given points on a curve in order in this way to determine the subtangent, etc. One can understand his satisfaction at a discovery which met the one object of universal scientific interest at the time, and it was so purely geometrical that it vastly surpassed the merely rule-bound method of his rivals cited above. He expressed it here. I'm not going to try reading the French. He bases his solution on the analytical equation of the right-angled triangle formed by 1. The ordinate of the point on the curve to which the required straight line in the problem should be drawn perpendicularly. 2. By this same straight line, the normal. 3. By that part of the axis cut off by the ordinate and the normal, the subnormal. Now, from the known equation of a curve, the value of either the ordinate or the abscissa is substituted in the equation of this triangle, the result being an equation of the second degree. And Descartes shows how even curves, of which the equations are of a higher degree, reduce to this, in which only one of the variables still occurs, indeed, as a square and in the first power. This is a quadratic equation, which makes its first appearance as a so-called impure equation. Descartes now observes that if the point assumed on the curve is imagined as the intersection of the curve and a circle, this circle will cut the curve at yet another point, and the result for the two unequal x's thus produced will be two equations with the same constants and of the same form, or else only one equation with unequal values of x. But there will be only one equation for the one triangle in which the hypotenuse is perpendicular to the curve, the normal. As we can imagine, if we let the two intersection points of a curve and circle coincide, and the circle therefore touches the curve. With that, however, the circumstance which makes for the unequal roots of the x or y of the quadratic equation also falls away. But now, in a quadratic equation of two equal roots, the coefficient of the term containing the unknown in the first power is double the single root, and this now yields an equation for obtaining the desired determinations. This procedure is indeed the brilliant stroke of a truly analytical mind. The merely asserted proportionality of the subtangent and the ordinate with the allegedly infinitely small so-called increments of the abscissa, and the ordinate pale in comparison. The final equation obtained in this way, in which the coefficient of the second term of the quadratic equation is equated with the double root, or the unknown, is the same as is obtained by the method of differential calculus. The differentiation of x squared minus ax minus b equals o gives a new equation, 2x minus a equals o, or x to the third power minus px minus q equals o gives 3x squared minus p equals o. Of course, the point can be made here that it is not by any means self-evident that such a derivative equation is also correct. Only a ratio, as remarked above, results from an equation of two variables which, just because they are variables, did not lose their character as unknowns, for the simple reason that by substituting the functions of power raising for the powers themselves, the value of the two terms of the equation are altered. And whether an equation still obtains between the two terms and their thus altered value is still, per se, unknown. All that the equation dy over dx expresses is that p is a ratio, and there is no otherwise real meaning to ascribe to dy over dx. But it is equally still unknown if this ratio equals p. To what other ratio it is equal. It is only the equation, the proportionality, that gives a value and meaning to it. Just as we said that this meaning, then a matter of application, is taken from elsewhere empirically, so with respect to the equations now at issue which are derived by differentiation, it is from elsewhere that we must know whether they have equal roots in order to find out whether the equation obtained is still correct. This is a circumstance, however, which the textbooks fail to bring to explicit notice. It is of course eliminated when an equation of one unknown reduced to zero is straightway equated with y, with the result, mind you, that by differentiation only a ratio, a dy over dx, is obtained. Of course, the calculus of functions should deal with the functions of power raising, while differential calculus with differentials. But it by no means follows from this as a matter of course that the magnitudes of which we take the differentials or functions of power raising would themselves also have to be only functions of other magnitudes. Besides, in the theoretical part, where it is shown how to derive the differentials, that is, the functions of power raising, there is still no indication that the magnitudes which we learn to manipulate in such a derivation are supposed to be themselves the functions of other magnitudes. Regarding the omission of the constant in differentiation, attention can further be drawn to the fact that the meaning of the omission here is that it makes no difference to the determination of the roots if these are equal, for this determination is exhausted by the coefficients of the second term of the equation. As in the cited example of Descartes, the constant is itself the square of the roots, which can therefore be determined by the constant as well as the coefficients. The constant being no less than the coefficients, simply the functions of the roots of the equation. In the usual exposition, the omission of the so-called constants, which are linked to the other terms only by the plus and minus signs, results from the mechanism of the procedure by which, in order to find the differential of a compound expression, an increment is assigned only to the variables, and the expression thereby formed is subtracted from the original. Nothing is said regarding the meaning of the constants and of their omission, the extent to which they are themselves functions, and, as such, do or do not serve any purpose. In connection with the omissions of the constants, a similar comment can be made regarding the names of differentiation and integration, as was earlier made regarding the expressions finite and infinite, namely, that the term says the opposite of what is intended. To differentiate indicates the positing of differences, whereas by being differentiated, an equation is in fact reduced to fewer dimensions. With the omission of the constant, a moment of determinateness is taken away, as we said. The roots of the variables are made equal, their difference, therefore, sublated. In integration, by contrast, the constant must be added back in again. The equation is thereby integrated. But, note well, only in the sense that the previously sublated differentiation of the roots is restored. What was posited as equal is differentiated again. The ordinary expression contributes to the obfuscation of the essential nature of the matter by directing the focus of attention to what is in fact subordinate, even alien to it. On the one hand, to the infinitely small difference, the increment, and the like. On the other hand, to the mere difference in general between the given and the derived function, without any indication of their specific, that is, qualitative, distinction. Another important area in which differential calculus is employed is mechanics. The meaning of the various power functions that result from the elementary equations of its subject matter, motion, has already been adumbrated in passing. I shall now take it up directly. The equation, that is, the mathematical expression, for plane uniform motion, parenthetical C equals S over T, or S equals CT, where the spaces traversed are proportional to the elapsed times according to an empirical unit of c, which is the magnitude of the velocity, offers no scope for differentiation. The coefficient c is already fully determined and known, and no further expansion of powers is admissible. We called attention earlier to how S equals AT squared. The equation of the motion of a falling body is analyzed. The first terms of the analysis, ds over dt equals 2at, is translated into language and accordingly into concrete existence to mean that we must suppose a term of a sum, a conception which we have long since abandoned. A term which is a part of a motion, specifically that it falls on the side of the force of inertia, that is, of absolutely uniform velocity, with the result that in infinitely small parts of time the motion is uniform, but in the finite parts, that is, in those actually existent, it is uneven. To be sure, Fs equals 2at, and the meaning of A and of T is known, and so, too, that the determination of the uniform velocity of a motion is thereby being posited. Since A equals S over T squared, 2at, is simply equal to 2S over T. But with that, absolutely nothing new is known. Only the false assumption that 2at is a part of the motion as a sum gives the false semblance of a physical proposition. The factor itself, a, the empirical unit, a quantum as such, is attributed to gravity. If the category of the force of gravity is used, then it ought rather to be said that the whole, S equals at squared, is the effect of gravity, or better, the law of it. The same goes for the proposition derived from ds over dt equals 2at, that if gravity ceased to act, then the body would attain, with the velocity reached at the end of its fall, twice the distance it had traversed, if the same period of time as the fall. Here, too, we find an unsound metaphysics. The end of the fall, or the end of a time period in which the body has fallen, is itself still a period of time. If it were not a time period, then rest would be assumed, and therefore no velocity. Velocity can only be calculated according to the distance traversed in a period of time, not at its end. And if now finally an application of differential calculus is made in other physical fields where there is no motion, as for example in the behavior of light, apart from what it is called its propagation in space, or in determining magnitudes with reference to colors, and the first function of a quadratic function is here also called a velocity, then this must be regarded an even more inadmissible formalism, a fiction of actual existence. We find the motion represented by the equation S equals at squared, says Lagrange, in the experience of falling bodies. The next simplest motion would be one of the equation S equals ct cubed. But no such motion is found in nature. We do not know what the coefficient c might mean. Although that might well be so, there is a motion nevertheless, of which the equation is s squared equals at, or s cubed equals at squared. This is Kepler's law of the motion of the bodies of the solar system. And what the meaning here of the first derived function, 2at over 3s squared, etc., might be, and the further direct manipulation of this equation by differentiation, the development of the laws and the determinations of the absolute motion from this starting point. All this must, on the contrary, appear indeed as an interesting problem, an opportunity for analysis to display its worth at its most brilliant. Thus, the application of differential calculus to the elementary equations of motions is not by itself of any real interest. The formal interest comes from the general mechanism of calculus. But this dissection of motion takes on another meaning in connection with the determination of its trajectory. If this trajectory is a curve and its equation contains higher powers, then there is need of transitions from the rectilinear functions, which are the functions of power raising, to the powers themselves. And since the functions are to be obtained by eliminating from the original equation of motion the factor of time which is contained in it, this factor is, at the same time, to be reduced to the lower functions of expansion, from which those linear equations can be obtained. Here, we are led to where the interest of the other part of calculus lies. The aim of the foregoing has been to highlight the simple, specific nature of differential calculus by defining it, and to demonstrate it in some elementary examples. Its nature has been found to consist in this: that the coefficient of the term of the expansion, the so-called first function, is obtained from an equation of power functions, and the relation which this first function represents is demonstrated in moments of the concrete subject matter, and these moments are themselves determined by the equation thereby obtained between two relations. We must, equally, consider in brief, regarding integral calculus, what can be learned of its specific concrete nature from the application of its principle. Taking stock of this calculus is already made simpler and more accurate by the fact that we no longer take it as the method of summation from which it got its name in opposition to differential calculus, in which the increment is taken to be the essential ingredient, and which gave to it the semblance of being essentially linked to the form of a series. The task of this calculus is, on the face of it, just as theoretical, or rather formalistic, as that of differential calculus. Although it is well known, it is the converse of the latter. Here, we begin with the function considered as derived, as the coefficient of the first term resulting from the expansion of an equation, as yet, however, unknown, and the original power function is to be derived from it. The function, which in the natural order of expansion would have to be considered as original, is here derived, and the one previously considered as derived is here the one given, or, in general, the one to start with. Now, the formal details of this operation seem to have already been attended to by differential calculus, where the transition from the original to the expansion function and the relation of the one to the other is established in general. Here, although in order to set up the function which is the starting point, or again, in order to effect the transition from it to the original, recourse must necessarily be made in many cases to the serial form. It is important, nevertheless, to keep in mind that, as such, this form has nothing directly to do with the proper principle of integration. Now, it is in view of the formalism of its operation that the other part of the task of calculus appears as the application of the operation. This is itself now the task, namely to find the meaning, in the above-mentioned sense, of the original function, the one considered as first by the given function of a particular object. It might seem that this doctrine, too, was in principle already settled in differential calculus, except for a further circumstance that comes into the picture and will not let the matter rest so simply. For, by finding out that in this calculus the linear relation is obtained through the first function of the equation, we also know that the integration of this relation yields the equation of the curve in the relation of abscissa and ordinate. Or, if the equation for the area enclosed by the curve were given, then regarding the meaning of the first function of this equation, we should have already learned from differential calculus that such a function displays the ordinate as a function of the abscissa, and therefore the equation of the curve. But now all comes down to determining which of the moments of the object is given in the equation itself. For an analytical manipulation can only start from what is given and then pass on to the determination of the rest of the object. For instance, what is given in the equation of the curve is not the equation of an area enclosed by that curve, nor of some supposed body arising from its rotation, nor again of an arc of the curve, but only the relation of the abscissa and ordinate. Consequently, the transitions from those determinations to this equation itself cannot yet be handled in differential calculus. It is reserved for integral calculus to find these relations. But, further, it has been shown that the differentiation of an equation of several variables yields the expansion power, or the differential coefficient, not as an equation but only as a ratio. The problem then is to find in the moments of the given object a second ratio, which is equal to this ratio, which is the derived function. By contrast, the object of integral calculus is the relation itself of the original function to the derived function, which is here presumed given. And the task is to assign in the object of the first function the meaning of the original function, yet to be found. Or rather, since this meaning, say the area enclosed by a curve or the rectification of a curve represented as rectilinear, is already declared to be the problem. The task is to show that such a determination is found by an original function. Also, to show which of the moments of the object is the one that must be assumed for the present purpose as the initial derivative function. Now, the usual method makes things easy for itself by representing the difference as one of infinitely small elements. Thus, for the squaring of curves, an infinitely small rectangle, the product of the ordinate in the element, that is, the infinitely small segment of the abscissa, is taken for the trapezium, which has as one of its sides the infinitely small arc opposite that infinitely small segment of the abscissa. The product is then integrated in the sense that the integral is said to give the sum of the infinitely small trapezia, or the surface of which the determination is being sought, namely, the finite magnitude of this element of the area. In the usual method, a right-angled triangle is likewise formed from the infinitely small elements of an arc, and the corresponding ordinate and abscissa. A triangle in which the square of the arc is said to have the equal sum of the squaring of both the other two elements, their integration yielding the arc as an infinite quantity. This procedure presupposes the general discovery on which this field of analysis rests, in this case inasmuch as the squared curve, or the rectified curve, etc., stands to a certain function given by the equation of the curve in the relation of the so-called original functions to the derivative. The point is to know, granted that a certain part of mathematical object, say a curve, is the derived function, which other part of the same object is expressed by the corresponding original function. It is known that when the function of the ordinate given by the equation of the curve is taken as the derived function, the corresponding original function is the quantitative expression of the area of the curve cut off by this ordinate. That when a certain tangential determination is considered the derivative function, its original function expresses the length of the arc that belongs to this tangential determination, etc. However, that these relations, the one of the original function to be derived, the other of the magnitudes of the two parts or circumstances of the mathematical object, that these constitute a proportion, the method that employs the infinitely small and operates with it mechanically spares itself the trouble of recognizing and demonstrating it. The true merit of mathematical acumen is that, from results already known elsewhere, it has found that certain sides of a mathematical object stand to each other in the relationship of original and derived function, and it has found which sides these are. Of these two functions, the derivative, or as has been defined, the function of power raising, is the one in this calculus which is the given, relative to the original which is to be found from it by integration. This derived function, however, is not immediately given, nor is it by itself already given which part or determination of the mathematical object should be considered as the derived function, in order that, by reducing it to the original, the other part or determination whose magnitude is being sought in the problem might be found. For the purpose of this problem, the usual method begins, as we said, simply by representing as infinitely small certain parts of the object, in the form of derived functions determinable by differentiation from the originally given equation of the object in general, like the infinitely small abscissae and ordinates in the rectification of a curve. From these parts, it then takes those which can in some way be linked by elementary mathematics with the matter of the problem, likewise represented as infinitely small. In our example, the arc. And by virtue of this connection, once the parts are known, that part is also determined of which the problem was to find the magnitude. Thus, for the rectification of curves, the three mentioned infinitely small parts of the object are linked together in the equation of the right-angled triangle. For while the squaring of curves, the ordinate is linked with the infinitely small abscissa to form a product. Since, in general arithmetic, an area is assumed to be the product of lines, the transition from such so-called elements of the area, the arc, etc., to the magnitudes of the area, the arc, etc., as such, passes then only for the ascent from the infinite to the finite expression, or to the sum of the infinitely many elements of which the required magnitude is supposed to consist. It is therefore only superficially that one can say that the problem of integral calculus is only the, albeit more difficult, converse of the problem of differential calculus. The real interest of integral calculus is directed rather exclusively at the reciprocal relation in concrete objects of original and derivative function. Also, in this part of calculus, Lagrange did not try just to smooth over the difficulty of the problem at hand with direct assumptions. Here, too, it will help to elucidate the nature of the issue if we give the essence of his method with the help of a few examples. The task of this method is still the same, to prove that between particular elements of a mathematical whole, e.g. a curve, a relation of original to derived function obtains. But now, in this field, the proof cannot go through directly, simply by virtue of the nature of the relation at issue. For the latter connects elements within the mathematical object which are qualitatively different. Curves with straight lines, linear dimensions and their functions with plane or plane dimensions and their functions, etc. The required determination can only be taken, therefore, as the mean between a greater and a lesser. With this, of course, the form of an increment with a plus or minus naturally comes into play again, and Lagrange's vigorous développement can be heard again. But we have already pointed out how the increments have here only arithmetical, infinite meaning. From the expansion of that condition, that the magnitude to be determined be greater than the one easily determinable limit and smaller than the other, it is then deduced that, e.g., the functions of the ordinate is the derived first function with respect to the function of the area. Lagrange's exposition of the rectification of curves, since it proceeds from the principle of Archimedes, involves the translation of the Archimedean method into the principle of modern analysis. And this affords us an insight into the inner, the true meaning of an endeavor which in the other method is carried out mechanically. The mode of procedure is necessarily analogous to the one just given, but Archimedes' principle, that the arc of a curve is greater than its chord and smaller than the sum of the two tangents drawn at the endpoints of the arc, and contained between these 2 points and the point of their intersection, does not yield any direct equation. Its translation into modern analytical form consists in the invention of an expression which is, per se, a simple fundamental equation, whereas in the earlier form the principle simply postulates alternating ad infinitum between terms each time determined as too great and too small, the successive advance only yielding new terms which are still too great and too small, albeit between always narrowing limits. On the basis of this formalism of the infinitely small, the equation dz squared equals dx squared plus dy squared is formulated without further ado. Lagrange's exposition, on the contrary, starting from this same basis, demonstrates that the length of the arc is the original function with respect to a derived function, the characteristic term of which is itself a function, coming from the relation of a derived function to the original function of the ordinate. The fact that the representation of the infinitely small occurs in the method of Archimedes just as later in Kepler's treatment of stereometric objects, has been adduced as authority for the employment of the infinitely small in differential calculus, without any thought being given to its distinctive peculiarities. The infinitely small signifies in the first instance the negation of the quantum as such, that is, of the so-called finite expression, of the completed determinateness that quantum as such possesses. Similarly, in the subsequent renowned methods of Valerius and Cavalieri, among others, methods which are based on the treatment of the relations of geometrical objects, the fundamental principle is that the quantum of the terms treated at the moment only in relation must, as such, be left out of account for this purpose, and the terms themselves be taken as non-quantitative. But, for one thing, these methods all fail to recognize and to bring to notice the affirmation that hides behind the merely negative determination. This is the affirmation which we saw earlier in abstract form as the qualitative determinateness of quantity, and, in more determined form, as the qualitative determinateness found in the relation of powers. And also, since this same relation of powers contains in turn an aggregate of more precisely determined relations, such as that of a power and its expansion function, these relations, also, would have in turn to be based on and derived from the general and negative determination of still the same infinitesimal. Now, in Lagrange's exposition just cited, the determinate moment of affirmation implicit in Archimedes' method of developing the problem is made explicit, with the result that a procedure otherwise affected by a limitless progression is given its due limit. The greatness of the modern discovery, in itself and in its capacity to solve hitherto intractable problems, and to handle in simpler fashion those previously soluble, is to be laid solely in the discovery of the relation of the original to the so-called derivative functions, and of those parts of a mathematical whole which stand in such a relation. These excursions may suffice for the purpose of highlighting what is distinctive about the relation of magnitudes, which is the subject matter of the particular kind of calculus under discussion. It was possible to limit them to simple problems, and the methods of solving them, nor would it have been expedient for the conceptual work which was our only concern here, or within this author's competency, to go over the whole compass of the so-called application of differential and integral calculus, to reduce all their problems and their solutions to the principle on which, as we have inductively shown, that application rests, and thereby to complete the inductive work itself. But what was said has sufficiently demonstrated that just as for each specific form of calculating there corresponds as subject matter a corresponding particular determinateness or relation of magnitude, such a relation as constitutes addition, multiplication, the raising of powers, and the extraction of roots, the operations with logarithms, series, etc. The same is the case for differential and integral calculus. For the object specific to the latter, the most suitable name might be that of the relation between a function of powers and the function of its expansion or potentiation, because it is the closest to what an insight into the nature of the subject matter suggests. Of course, calculus makes use, quite in general, of logarithms, of circular functions and series, especially in order to render more tractable expressions devised for the required operations of deriving the original functions from the functions of expansion, but it uses them in the same way as it uses the operations involved in the other relations of magnitude, such as addition, etc. Calculus, whether differential or integral, has indeed a more specializing interest in common with the form of series, namely that of determining the functions of expansion, which in the series are called coefficients of the terms. But whereas the interest of calculus only expands to the relation of the original functions to the closest coefficient of its expansion, The aim of the series is to display as a sum aggregates of terms ordered according to the powers fitted with those coefficients. The infinite of the infinite series, the indeterminate expression of the negativity of the quantum in general, has nothing in common with the affirmative determination present in the infinite of calculus. The same is the case for the infinitesimal, the increment by means of which the expansion happens in the form of a series. It is only an external means for that expansion, and its so-called infinity either has only the meaning of such a means or has none at all. The series, since in fact it is not what is being sought, brings with it a de trop, which then creates the otherwise superfluous trouble of eliminating it. The method of Lagrange has again privileged this form of series, and is therefore burdened by that trouble, even though it is by virtue of that method that the true character of what is called the application is brought out in the latter, for it directly demonstrates, without imposing the forms of dx, dy, etc. unto the objects, to which part of these objects the determinateness of the derived function of expansion, belongs. And it transpires thereby that the form of series is not what is truly at issue here. And that is going to bring us to the end of Quantum Remark 2. I didn't have a whole lot to add, so hopefully I didn't add a lot of confusion. There was a good bit there. Not having a good understanding of calculus limits me from being able to expound upon any of this. But I do derive from this what he is talking about. The negation of terms, the adding in of unnecessary steps is what he is really calling out here. Why are you adding this in only to remove it later? And that makes sense to me, right? If this is irrelevant, why are you calculating it? That part of it absolutely makes sense. But again, I don't have the full understanding of calculus, either derivative or what was the other one? Derivative, and I lost it that fast. Anyway, either one of the two forms of calculus, I'm not familiar with either one of them, even though I could probably do the work if it had to be done. It is not something which I find all that entertaining, so I'm not going to do a deep dive into calculus. This is probably as close as we're going to get. But I can see what he is talking about as he goes through, and hopefully you can too. This one was more of a reading into the record than it was of an expounding or a clarifying, simply because I don't have the information from which to clarify, right? If there was anything wrong with this, I don't have the technical knowledge to tell you that there is something wrong with it. And so I just hold my peace. This was about reading it. There will be other things that we can discuss at a later date. If you like what I'm doing over here, let me know down below. Give me a like, a share, a follow. Throw me a comment if you agree or disagree, or if you have some clarification to add, drop it in the box down below. And if it remains respectful, it gets to remain up. If there is another work you would like me to read or to discuss, drop that in the box as well. And if you really like what I'm doing, hit me with that super thanks, a membership, or buy my book at the link provided down below. To the crew, thanks for hanging out. I appreciate every single minute that you are here with me, and I am praying for you every single day. Until next time, I love you. God loves you. You are perfect, whole, and complete, just the way that you are. And this has been Pitt State. Peace.